All right, welcome back to the slides on the big three. Let's finish them up. Remember what the big three are. We've got our destructor, which is called when our object goes away, the copy constructor, when you're building an object of your class's type using an old one. You want to copy an old one into the new one that you're creating. And then the copy assignment is kind of almost the copy constructor. It's just you've already got an object, you've already constructed it in some way, but you're tired of what it holds and you want to bring somebody else's stuff. You want to copy them into you. All right. So we know about the defaults. We know that the defaults are sometimes not the best. With our box class, we learned about that. And before we continue today, I do want to just say something that's like general OOP stuff. It's a common error that I see in CSCI 41 students. It's when you use a local variable and you use the same name, you make accidentally a local variable that has the same name as a member variable, and that's not good. That shadows the member variable that you probably wanted to mess with, okay? So here is a very common example that I see among CSCI 40 students. So here's a class and the set blah is incorrect. Do you see it? So if I made a foo object called f, and let's say what that does, right, is it makes this thing in memory and it has space for all of its member variables, which is just one int called blah. So there it is. It's set to garbage because I don't have a normal constructor. And let's say I come along and I say f dot set blah to 42. What we'd like to have happen is this, but this code will not do that. Do you see why? It's because I said int. This right here, by saying int, by saying the type name, you've just made a brand new variable. Does that make sense? This creates a brand new local variable, and it's going to shadow the one you really wanted to mess with, your private member variable with the same name. Does that make sense? So inside of the call to set blah on the stack, it's going to make a local variable called blah. Whereas if you had just said blah by itself, you would have been touching the one you cared about, set it to 42 or whatever. But now that you said int blah equals x, you've made a local variable on the stack for the duration of just this call only that is going to go away once the call is over, and we've never really set our member variable. Do you see the problem there? And so that is unfortunate, and that is difficult. This is also something that you could use the initializer list to fix. Notice if this is part of a constructor, at least. If this was a constructor, you could have used the initializer list, because you always, after the colon, you always can say the name of one thing, and that is a member variable. The member variable goes first, and then something else can go second, like the thing you want it to be. And so sometimes in constructors, I like to give parameters, like if you want to set a member variable, I like to give a parameter with the same name, and it doesn't actually shadow things if you use the initializer list. Like that could have been a parameter, and it's going to set a member variable. All right, so I've shown you some examples of that before, but that's kind of the idea. And so that's a common pattern for constructors, at least, using the initializer list to set a member variable to a parameter that has the same name, but there is no ambiguity if you use an initializer list, because you can use the same name twice, and this one is always, the first thing you say is always the name of a member variable in an initializer list. But for set blah, you just have to remember to not say int, okay? And that will fix the problem. Do you see it? Will we not make this mistake in the future? I hope so. So yeah, with that in mind, let's go back to the big three. We noticed that for our box implementation, weird things were happening. And we noticed that there was an issue with the destructor originally, if you remember the stuff from last time. Let's just look at it real quick. It was, lecture 5's box correct. The very first thing we noticed was something's going wrong with the destructor because we're leaking memory. So let's remember to delete our value. And then weird things happened after that caused like double deletions of things. And then we came along and we noticed there was also something like we needed to change in the copy constructor and the copy assignment operator. Yeah. So remember those things. And that's actually a rule. All right. So usually when you start using the heap, start dynamically allocating your own memory, the default implementations of the big three, they break down because they're going to do shallow copies. Remember the difference? They're going to do shallow copies, which was the opposite of what we wanted, right? We wanted a deep copy, but the default implementations of the big three don't really do that. And they also leak memory for the destructor, okay? So there's something called the rule of three, and that is the second you notice that you have overloaded one of these guys, like, oh, I noticed that there's something wrong with the destructor, let me change that. Oh, there's something wrong with the copy constructor, the default. Let me override that and do it the way I think it should be done. There's something wrong with the copy assignment operator. The second you get one of those and you notice that something needs to change and you change it, you should probably overload all three of them because they go hand in hand. And I hope you see, right? That's what happened last time. And this is just making sure you don't have any memory problems down the line. Usually the issue is when you've started to include pointers, which are indirect references to things. Usually you want deep copies and not shallow copies, okay? So that's what's going on. There are other things. This is like a standard practice in C++. It's called the rule of three. It's noticing this. There's other ones. There's called the rule of zero, which is if you just use objects as your member variables and you don't like use the heap yourself or anything like that, C++ will take care of everything because like the destructor will just get called for your member variables as they're trying to go away. So if you don't allocate any of your own memory, usually you don't have to change any of the copy constructor or the copy assignment or the destructor. Like C++ will deal with it for you if you don't allocate anything. There's also something called the rule of phi, which is a little bit fancier. There's something called the move constructor and move assignment that came out like over a decade ago from the C++ 11 standard. And yeah, it's a little bit more complicated. I encourage you to go and look it up. Moving is different from copying in that you can steal an object's memory as it's about to go away. That's what the idea of a move is, but I highly encourage you to go and read more into that. But I just wanted to talk about the big three for these lectures, all right? But look into the move constructor and move assignment if you're interested. You can steal somebody's memory. And with that, I want to make us think about our vec class from the lab where we're making our own vectors. Because we didn't overload anything, right? We're using the default destructor, copy assignment operator, and copy constructor. Are any of those wrong? If so, tell me which ones and why. Can you think about that? Go back to the code. Let's think about this. So you make a vec v. What does the constructor do, right? It's going to make memory on the heap, isn't it? And so eventually one day, right, when you're done with your vector v, you've got an array on the heap. This is just like our box, right? Same problem. When the vector v goes away with a blank default destructor, this guy is gone. The address of the thing on the heap is gone, but this isn't gone. So we're leaking memory for sure in our vec class right now. Do you see it? And I just told you this in a slide. The second one thing's wrong, all the others are wrong too. All right, so there's also an issue with our copy assignment and copy constructor, and I hope you see it's the same exact problem as with box. It's just like we're using an array rather than just a single int. So like say I come along and I say vec v2, make it out of v, assume that I didn't get rid of it yet. Then or let me just draw a new picture. So here is, let's say I've got vec v, it's got an array, right? In addition to other things. And let's say that array on the heap, I don't know, it lives over here. Here's the heap array, and it lives at address 100. So R holds 100. The default implementation of the copy constructor is going to make v2's R set to whatever v's R was, right? And that's the same address. It's copying the things in the member variables themselves. So it's whatever this box is, whatever this box is, which is 100. And so that's a shallow copy. Do you see that? That's not good. And then for similar reasons, I think you can imagine another issue is going to happen with the same kind of issue is going to happen if you like make a vector v3 and you eventually use the copy assignment. Try to draw a picture of that because it's the same exact problem, yeah? And so we're doing shallow copies and leaking memory, yeah? All three are bad. And that is the rule of three at large. So that's great, okay? So that means then we need a part 2 to our vector lab, All right. So that is why the first lab on vectors was just like getting it working, getting all the normal vector only things working, but now we need to make it correct, right? Make it handle its memory properly. So let me show you your next lab's vec.each file. Let me copy that in. Dun, dun, dun. So let's copy. It's in a weird place on my own computer. It's in starter code 41. I think it's 2. Yeah, let's do vec.each. And I'll eventually explain this in a future lab video, of course. But here it is. And I copied it to here, right? Yeah. Here it is. It's all the old stuff. You got resize, same member variables, right? Same member variables, mostly the same methods. It's just we've added the big 3, all right? For the copy assignment operator, sometimes people add this thing called no except. It's a very common thing in copy assignment operators. It's just you, kind of like const, it's a marker to your method. It's you promising to not throw an exception in the body of this method. So you just implement it, just kind of like pretend no except was const. You'd still put it in your implementation, okay? So yeah, that is there. And we are going to implement these, all right? I'm gonna ask you to implement those for your vec lab. All right, for your next lab, for part 2. And let's figure out what needs to happen. All right, I think you can kind of see it's just going to be the same stuff as we were doing in the box example from last time, but it's good to draw pictures, right? So the destructor needs to change because we're currently leaking memory, right? The array that we're holding doesn't get deleted properly. It's just going to stay there. So say this was our code, and in the closing brace for where this vector v lived, this vec v lived, here's what's going to happen by default, right? We have like that vector v is going away, so you've got like your num items, your capacity, and then you've got your array, and the array is pointing to a place on the heap. Boop. What we want to do, because the default is just like it gets rid of vector v's memory, which does not worry about the heap. What we would like to do is delete the array inside of the destructor so that when the vector v goes away, so does this guy. Yeah, that's what we want. So the way that we get rid of an array on the heap is you say not just delete r, but it's delete bracket bracket, right? R. So that will cause that to go away. Then everybody else will just properly get removed as the object gets destructed, okay? And yeah, that's the goal. And the reason we want to do that and not leak memory is say you did this like in a giant loop, right? Say you, for 1,000,000 times you made a vector, filled it up, and then it got destructed, but the default destructor leaked the memory that was on the heap. So we're leaking millions of arrays, right? If we did this inside of a loop, and that's not good. So that's one thing gotta watch out for. And let's see, what else? Yeah, so as we're implementing this, here's like what we want here. What we want to do to implement this is the following. I'll steal my picture because it's gonna come up again. Move it on over. So yeah, it's the heap memory that we need to worry about inside of the destructor. All of our member variables are automatically about to go away. That's just what it means to have an object reclaimed, to have an object go away. So it's really just R that we have to worry about, which points to a place on the heap. And yeah, the destructor is going to get called when we're done with this object. So we're done with this thing on the heap. We want to get rid of it. We want to delete bracket bracket R. And don't forget the brackets. The reason we need that is because R is just an int star. Right? It's just an int star, and so C++ doesn't know by default, like was that a single int on the heap that you're trying to get rid of, or was it a big long array? We have to remind it, no, this was an array. Go remember how long it was, okay? Because it keeps some of that data in like a little heap database secretly. So yeah, that's what needs to happen. And so we're going to delete bracket bracket R, and then V will be reclaimed by C++. So that's good. So that's the destructor. Copy constructor. Let me show you what we need. We need a deep copy, right? So what needs to happen? Let's say we've got a vector v and we've pushed back to these 3 things. So you see what's going to happen to v? It's going to have its member variables. It's going to have the array. It's going to have num items and capacity. capacity. If you think about it, it's going to look like this. It's going to end up being of size 4. Right, so the capacity is going to be 4, but we put 3 things into it, the 1, the 2, the 3. And let's say that this array lived at address 100, so R is looking like that. And this was on the heap, right? This was on the heap, and yeah, that's going to be our vector v. And if we want to make v2 in v's image, we want to do this. v2. What we'd like to do is num items. It needs to have the same num items and capacity, right? So this still needs to be 3 and 4, but we don't want to do that. Yeah, we don't want to do that. We want to give it its own version of the same array. So we're going to make a brand new array on the heap of the same capacity, and then copy over all of those things, right? So this is shiny and new, just for v2. This is a deep copy, yeah? And we're going to copy over all of the num items of the old vector, right? I guess you could look at num items there too. So yeah, it's going to be 1, 2, 3. You can skip this last one. It's just garbage anyway. That's what we want, okay? That's what we want. That's how the copy constructor should work. So you copy over the ints, that's fine. But the array should not just like copy address 100 and have it point there. We would like to make our own array on the heap of the same size, okay? Same size. That is our goal, okay? And yeah, that's in picture form and word form. This is, yeah, we're getting called, we have the other vector and it's called other, right? That's what we've called our other parameter. This thing that we're trying to copy from is called other. That's exactly how it worked in the box implementation. And so what we want to do is set our member variables to others' member variables, but deep copying things that need to be deep copied. Like num items and capacity, those are just already ints. So you can just be like num items equals others num items. Capacity equals others capacity. Yeah, that's good. But R's, you cannot just be like my R is equal to others R, because that would do a shallow copy, right? So yeah, R needs some work. You need to make a new array on the heap with the same capacity, and then copy all the elements from the others array into our own. And we've already did this, right? We've already done this in the resize method. And this is very similar to the kind of thing you already did in the resize method. So you can probably copy and paste some of your code from that if you chose to implement it. Use the case 2 of your pushback. If you chose to implement that using the resize method that I gave you and asked you to try out. So yeah, that's copy constructor. And then we got copy assignment operator, which is slightly similar to the copy constructor, just like you need to do the self-assignment check. There's other things that are involved, right? But it's still going to be deep copy, very similar to copy constructor. We've got, in my example that I want to draw, because again, I just want to draw a lot of pictures for you in this class, and then it's your job to implement those pictures. That's what we're going to get good at. So vector v and v2 are being default constructed. We've got an array, v has an array, v has a num items, I'll just say ni for short, and then cap I keep saying as the shorthand for capacity. And let's say, so 42 and 43 are going into v, so let me just show the final product of that. That'll be 42 and 43. We'll have filled this up. It'll end up being num items 2 and capacity 2, if you just follow the code that we did from last time that you implemented. And then v2 will start out default constructed, and then we're going to add 44. So I want to draw the state of memory that's like right here before the line runs. Okay, so it has its own R, it has its own num items, it has its own capacity, and it's just going to hold one thing, right? Num items capacity 1. The array on the heap is holding 44 right now. And then we come along and we say this line. So what needs to happen for copy assignment? Well, first is self-assignment check. Make sure that we're not saying like v2 equals v2. Just bail out if that's what's happening. That's wrong. We don't want to try anything. We are already ourselves. But no, these are two different vectors in memory. They're good. You're good to copy v stuff into v2 using a deep copy. And so the first step is, like notice, and this is why I told you to just delete your old stuff. That's why I recommended that for the box implementation, because we don't even have enough room in the array. Like we can't just like reuse our current array to add the two things from V. So kind of the standard way of doing it is, all right, once we've made it past the self-assignment check, delete all of our own stuff. Get rid of it. Like this guy, go away. Get rid of that old array. Get rid of that. Then we're good to do everything that we did in the copy constructor. Okay, so then we're going to copy all the normal variables that don't need to be deep copied. That just like have their own memory already. We're going to copy those in. So bring the 2's in for the num items and capacity, and then deal with the array in the same way that we dealt with it for the copy constructor. Right. So array is going to become a new array of the capacity that we care about now, which is 2 from the others from V's. And then we're going to fill in all of these items into our own private version of that array. Does that make sense? That's what's going to need to happen. So you're going to get rid of your old stuff, and then you can do copy assignment things. Sorry, copy constructor stuff. All this all over again, okay? After making it past the self-assignment check first, though. Okay, so yeah, that's kind of the order. Check for self-assignment, return early. If you're going to try to, if you're assigning yourselves to yourselves, like V equals V, there's no work to do, right? That's supposed to be V. Sorry, it looked like a U. So there's that. And then, yeah, because you're getting rid of your own stuff, you're copying somebody else into you, then all your current stuff doesn't matter. So delete anything that you have on the heap, allocated since it's going away and we might have the wrong size anyway. So we'll delete our array, getting ready to make a new version of the correct capacity, right? Then we can just do everything we did in the copy constructor and we're set, okay? That's pretty much it. I hope that makes sense. So once you understand it, right? Once you see how these pictures kind of unfold, the code isn't going to be that bad. It's going to be very similar to the box example. There won't be too much that changes. I hope you see the importance of this, though. We want to make sure that our memory is being dealt with properly, because it really isn't correct, our old version of vectors. So let's make sure it's right in the next version of our lab. And yeah, let's see. I've got a few slides left about random things. The first one is still on topic, so there's definitely time. So please pause the video and try the following. From last time, we've got the it was the box correct example, right? So it's like lecture 5. In lecture 5, you go to the lecture 5 code from class, go and look at the box correct.cpp file. That's the code. I'd like you to update that box class and have it hold 2 things instead of 1 on the heap. Let it have a constructor that lets you set the 2 things, like make an int called holding 42 on the heap and 43 on the heap. So instead of just 1 value on the heap, let it hold 2 values. So like the constructor should do this. So running this line should make an object B that holds on to, like, let's call them val1 and val2. Those are going to hold on to 2 ints on the heap. So val1 will hold on to 42, val2 will hold on to 43. See that? So do that, add a second val, and rename the first one to val1, and update the big 3, like update the constructor too, of course, and update the big 3 so that there aren't any memory leaks, because you know that there will be one by default. So go fix that. Remember that the destructor needs to delete the second value, and the first one's also changed names because we're dealing with 2. Same with copy assignment. That's the right way to do it. It's just a good pattern. Just like delete your old stuff, bring in new stuff, make it on the heap again. And yeah, remember that the copy constructor and copy assignment, they have to copy a new value. We used to be copying like this guy's, the val1s, but let's also copy the val2s, all right? So you have to make room for that on the heap and fill it in with the right values. Can you try that? I think this would be a very good exercise to see if you've got it in your head properly. And so, assuming you give it a good try, I'll do it too. Boop. So I'll copy it into this file, this folder for today, and I'll call it box with 2 things. So that's where I'll put it. Box with 2 things. And so let's go and change, I guess the first thing I want to change is what we're holding on to. Oops, sorry, I made a new tab for no reason. So this is going to be val1. Now we also are going to have a val2. Yeah, and then for our constructor, let's hold on. Let's ask for what values we want these things to hold. So we'll be like val1 could be 0, int val2 can be 0 by default unless sorry, these are supposed to be commas. There. And this could get us away with both a parameterized and a default constructor. If we say nothing, we'll set val1 and val2 to 0. But notice that these are local variables. These are parameters with the same names as my member variables. I want to show you the cool thing that you could do using initializer list. There's not going to be any ambiguity. I won't shadow anything if I do it this kind of way. And I'll show that to you. All right. So that'll be fun. And we'll go from there. So that's a good start. And instead of get val and set val, it's gotta be like get val1, set val1, get val2, set val2, right? So we need those. And I think that's a good start. And then, yeah, let's deal with these things. So that's int val1, int val2. You can only give the defaults one place, so I'll do it in the definition. And then we're setting val1 and val2, right? So val1 is going to be a new int set to whatever val1 is, but this isn't going to work, right? So this line won't work at all because val1 is not talking about my member variable if I've made a local variable like this, all right? This one takes priority now. Now when I say val1, I'm getting this one. Unless I go through this, that's one way to do it. I could say it like this, all right? That's one option. So I could set val1 and val2 like this. I can go through this because that's automatically getting my member variable. And like this one is like defaulting to the parameters again. That's fine. I could do it like that, or I could do it in the initializer list. I could say my val1 member variable, because always the first thing you say in the initializer list is the name of a member variable. And then here is a constructor call, right? And so for int stars, you can just give it a value that you want it to be. Just like, hey, make this a new int holding val1, and val1 is now whatever is taking precedence, which is the parameter, crazy enough. So this val1 is automatically talking about a member variable. This one is just like whatever is alive, that has precedence, which is our which is our parameter. Crazy. So this is going to work. This is going to set my member variable val1 to the parameter val1 on the heap, making a new place on the heap for it. So val2, new int. So for the same reason as these lines, it's essentially doing the same thing, is doing the exact same thing as these two lines. All right, so that's my updated constructor. And then I'm doing get val1 and get val2, right? So star val1, set val1, star val1, cool. And then we've got same for the val2s. Val2, dereference val2, set val2. Change the thing there. That's good. Then we've got the destructor, and we will say delete val1 and val2. Got to get rid of both of them, right? And then copy constructor, we're gonna similarly copy in the others val1 using a deep copy. Yeah. Using a deep copy for that one and for val2, then it's happy. And then for copy assignment, same idea, right? Self-assignment check, don't forget about that. And then copy assignment for everybody after we've deleted our old stuff. So delete val1, like that's a standard way of doing it. Though you know that you can just reuse the int stuff just to make it so that it's going to work for any kind of object, including things like this for our vectors. A good pattern is to just like delete your old stuff, make it all new again by copying kind of what you did in the copy constructor. So yeah, delete your old stuff. So it's kind of a combination of destructor plus copy constructor. So there's that. And yeah, I can just literally can copy these guys. There we go. And yeah, got to return a reference to yourself still. That should work. And val +1 is a function that makes no sense anymore. And let's let's do what we can. So like B1, set val 1, and set val 2. Cool. And call the copy constructor B2 set val 1, set val 2. So like let's set them to different things so that we see like changes. So this can be 42, this can be 43, 44, 45. Box B3. Let's set B3 to B2, and then do a self-assignment check. Make sure we're not messing things up and deleting ourselves. So let's be like B3 equals B3. That would work. And then B3, let's set its val 1 and val 2 to be like different things. 40, 45, and 46. So now when I print things, they should all be different, right? Because they're not linked anymore. They're deep copies. So like B1's val 1, B2's val 1, B3's val 1, and then print their val 2's as well. So if we did this right, what should we see? We should see 42, 44, 45, 43. Oh, sorry, this should be 46, huh? 46 and 47. So we should see then 42, 44, 46 on the first line, and then 43, 45, 47 on the second line. Yeah? Let's see. Oops, box with two things. We're getting there, close. But it looks like I did mess something up. B1. Oh, sorry, I set val 1 there. That was my fault, I think. Let's find out. Yeah, we got even numbers and odd numbers. It looks like it's working. Good. And then we can also make sure that by val grinding that we didn't leak anything. All heap blocks were free. No leaks are possible. Beautiful. Awesome. And so this was the call to val grind. Val grind -- leak check equals full. And then you pretend to run your program, and it runs through this program called val grind that checks for memory leaks, among other things. That's neat. And I think that was the example. So yeah, check do your own version first. I hope you did, and then compare it to mine. All right. And I think that should do it. That's all the code I want to write today. The last thing I want to do with the remaining slides, it'll just be really quick, is I want to go over every single data structure we're going to learn in this class throughout the semester so that you've heard their names once. I think that's useful, and I hope you agree. And the first is arrays, and you already know about them, so that's great. We've already covered those. There's not much left to be said about arrays, but you can explain it in a lot of detail right now, can't you? You can be like, all right, an array is a variable kind of with one name that you know exactly what the memory looks like, right? It's holding on to a bunch of values of the same type, and they're all contiguous in memory, yeah? So like if I knew that this was an array of ints and it held like 1, 2, 3 or something, if I knew that the starting address of A was 100, I know that the next element is at 104 because ints are 4 bytes long. I know that the next int in this array is at address 108. I know the way this memory works. Everything's right next to each other. And that's the reason I can do this kind of syntax, because what C++ is doing is calculating an offset from the base address. That's how it gets somewhere really quickly. That's how it can get to the middle of an array and know like that it's actually still part of the array, right? So you know how to describe an array, which is great, all right? And we've used those on the heap to make vectors. So you can use arrays to make some cool, to implement some cool abstract data types, or ADTs, right? You know that they implement vectors. The next one that we're going to care a lot about is called a linked list. And this may be something that you read about in CSCI 40. Don't worry if it wasn't, but this is what it looks like. A linked list is similar to an array in that you're holding a bunch of values and there's an order to the values, but they aren't going to be contiguous in memory anymore. They're going to be kind of like follow the leader, where each piece, like this is meant to be a linked list that holds on to the numbers 30, 47, 53, 26, and 74 in that order, okay? And there is a C++ type, just like there's a C++ vector type. There's a C++ list type that kind of wraps around this idea. There's a list of ints. Maybe you've used that before. And yeah, each piece of a linked list is called a node, and those are the things that are like one chunk. The rest are like, the way that you move around the list is each node of the linked list contains in the second half of it, the address of the next node. So you can dereference that and get to this guy. Then to know where to go next, you look at the next part, the next address part, and you go to that address, and that's how you move around the list. So these nodes can be in weird places in memory. They don't have to be next to each other. Just by following these next pointers, you can move to where you need to move. Pointing, right? It's pointing to the right spot. I hope that makes sense. Yeah, so each of these individual things, they're called nodes again. Each node of a linked list looks like this. Struct a node. They're holding on to the following. They're holding on to some sort of data. In this case, it's integers. And then they tell you how to get to the next node using pointers. And so that's the type of that's going to be node star next, which is a little weird because we are using the data structure inside of its own definition. It's called a recursive type. Isn't that weird? It's pretty cool. And that's okay. It's not infinite because it's you're kind of cutting off the infinity with the address with using a pointer. So that's nice. That works out. And then also the way that you mark that the list is over, that there's nothing left, is you use the special address where you know that you can't go there. That's the 0 address. That's called the null address, right? So use the null pointer to mark the end of the list. And usually you keep track of linked lists by saying where they begin and where they end, the first node and the last node. And so there they are. And it's really hard to get to the middle of a linked list. I hope you see you kind of have to start it first and make your way to the middle, which is going to take some time. You can't immediately calculate where the middle node is because it could be anywhere. It's like usually you make these nodes on the heap, all right? So that's unfortunate. It's harder to move around the list efficiently if you want to get to like the middle, but there's a trade-off. Arrays are good at some things. They're good at accessing like the middle, but they're really bad at like adding a number at the start, right? Because if you wanted a number at the start of this array, you have to like move that guy over, move that guy over, move that guy over in the opposite way, right? That's disgusting. That takes a while. But linked lists, the trade-off is it's hard to get to the middle, but it's very easy to insert a value anywhere once you have the node like before you want to put the thing. So say I want to add the node 42 right after 47. So I want it to go 30, 47, 42, then 53. Look at how easy that is. Make a node, have it hold 42 in its data, set the next to 53, and then change 47's next to that node. I didn't have to shuffle things over like I would have had to do here, like move the 3, then move the 2, then move the 1. Now there's room. You don't have to do that at all in a linked list. So that's quite nice. So there's a bunch of pointers all over the place, and so you have to get very comfortable with pointers. If you hate them, I'm so sorry. You're going to learn to love pointers one way or another in this class. You're going to get used to them. And this allows for a cool different way of holding numbers that makes certain operations that were hard with vectors and arrays easier. All right, it's like easy to get rid of like the first node in the list as well. You just kind of like change the pointer to its next. Ta-da! That's so interesting. So it's good. It's fun to read about and learn about, and that's where we're going next. So that's a linked list. Another kind of data structure that we care about will be called a hash table. And all it really is, all a hash table is, it's just a fancy lookup table. A lookup table, which deep down is honestly just an array. It's just a really fancy array. And the way we know how to get to which index is through a special thing called a hash function, which we'll talk about. But these exist in C++'s standard library as well. They're called the unordered maps. So if you've used an unordered map in C++, it's wrapping around a hash table data structure. So a good example of a hash table is a phone book. Remember those things? Or maybe you've heard about them. A phone book is something that takes a person's name to their phone number, right? So there's a concept of a key type and a value type in a hash table, in a map kind of thing. So these are the keys, these are the values. So you give me a string, I'll give you back an int. That's kind of what that's saying, all right? So a hash table supports the idea of like, all right, John Smith, his phone number, we can get to that and we can store it in a secret array, all right? Lisa Smith, we can figure out the index in the lookup table array where Lisa Smith's phone number is. So it's a string as input, and it's a integer as output. Does that make sense? That's quite neat. So there's a way to look up things, all right? And like Sandra D, there's a way to go from her name to an index in your array. And indexes of arrays are just numbers, so there's got to be a way then to take Sandra D and calculate 14. There's got to be a way to go from Lisa Smith and calculate 0, 1, John Smith to 0, 2, because that will take you to the index in the lookup table where they live, right? Because array indices are only numbers. So the way that you go from a string to an int, an int index, excuse me, and then you can store whatever you want at that index, is called a hash function. So there's a way to write a function that can turn like a string into some number that you can then use as the index of a table, of an array. Okay, so yeah, hash tables are good for like storing values and then looking them up later, looking up keys later, setting them equal to some value. All right, and there isn't really any context of like things in an order. It's just like I look up things and I get the answer back if they're in there. So hash tables are very, very fast for the things that they support, but they support different operations than arrays and lists. They're solving a different problem, okay? They're looking stuff up. So as a hash table, of course, we'll cover all of these in detail, so feel free to ask me questions earlier or read ahead, but this is where we're going. Another data structure that we're going to like is a binary tree, which is like a linked list, but maybe better or worse, depending on how much you like pointers, because there's going to be pointers all day long, all right? So a binary tree is like a linked list with 2 next pointers, a left and a right. So I can go, this is a node, each binary tree element is called a node again, just like for linked lists. And then you can either go left or you can go right. It's called binary for that reason. There's 2 options, left or right. And you can store a bunch of things and you can easily get around places because there's there's ways to order this stuff that you put into it in a nice way. So it makes things fast to search. Because like you got 2 options. It doesn't have to be like next. It can be either to the left or to the right. So it's very easy to like get places fast. We've got 2 options instead of 1. So it's like logarithmic, if that makes sense. Because you've learned about maybe binary search by now, similar to binary search. And there can also be a sense of order. Can have a sense of order in a binary tree. So it can kind of sort stuff for you, maybe, in a sense. Again, I'm being purposefully vague right now, and we'll go into more depth later. But yeah, this is a binary tree like that starts a place. So the starting point of a binary tree is called its root, because like the metaphor is it's a tree, like it's like the roots of a tree, or it's like an upside down tree. But the root of the tree is the first node in it, and then from there you can get to everybody by going some combination of lefts and rights. Okay, so that's how that works. And yeah, so this is what each node of a binary tree looks like. Again, they hold on to some kind of data, which can be any type. Doesn't have to be an int, but in this example on the slide, it's an int. Int data. And then we need to be able to go left and right. And the things that we see to the left and right of us are more nodes, and those are pointers getting us there. So it's a node star left and node star right. Okay, so that's that. That's a node data structure for binary trees at least. And then the way you know that you can't go left or right anymore is like you're gonna put the null pointer again. You're just gonna say there's nothing to the left of me. There's nothing to the right of me. There's nothing to the right of the 9. And so null pointers for just like for linked lists will mark the end. You can't go any further. But it's a cute little metaphor. Looks like a tree, and so the first node is called the root. All right, so we'll go to that. Next, we'll study heaps. A heap is unfortunately an overloaded term in computer science. It's not the same as the heap. There's a heap data structure that has nothing at all, unfortunately, to do with the heap that was like storing dynamic stuff, dynamically allocated anythings. The heap is a special kind of binary tree that stores things in a fun way. It's like it's always balanced and a little bit left-leaning maybe, and the thing that's at the root node is always either the maximum or the minimum. So heaps, the problem they solve is easily finding the maximum or minimum of a set of values that you've placed into it. So this value is always either maximal or minimal. And then there's a way to like, all right, get rid of that one, bring in the next one, and keep it so that the maximum is quick to find. Like then 89 will win, of course. So that's the idea. So it's very fast to extract. To extract the max or the min that you're trying to keep track of. All right, I hope that makes sense. And because we're optimizing extracting the max or the min, we're throwing away the order that we inserted things. It's different from lists and arrays and hash tables. It's solving a different problem. All right, but we're going to learn about it. It's going to be great. All right, and yeah, those are the data structures we will study in this class in detail. And you may be asking, like, what's the point of all of this? Well, this class is about data structures. It will help you with your critical thinking, first of all, and then also we can make some really fancy abstract data types out of combinations of these data structures. I will show you some, okay? It's going to be great. Do realize that not each of these is like the world's greatest thing. It's each of these data structures solves a problem. It's fast at doing the things that it's good at and slow at doing the things that it's bad at, or it's like those things are impossible. There's no concept of like an index in a binary tree, right? For example, but you could maybe do something similar. It's just not quite the same. All right. There's no there's no way to get to the middle of a linked list very easily, like I said. Okay, so there's some things you can't even do. Some things are just slow. Okay, but there's trade-offs. By making some things slow, you can make other things very fast compared to other things that you know about. And yeah, with that, we'll see a bunch of different computational complexities and learn to analyze things better, because that's going to make us a better programmer. And yeah, kind of the goal of this class is to know when to use which data structure, learn how to combine data structures to solve a problem, and how to analyze the efficiency, because you want to be picking the right data structures that give you the maximum efficiency, all right, in terms of space complexity or time complexity, all right? So that's going to be always important to us. Yeah, this isn't CSCI 40 where we just want to solve the problem. We want to solve the problem in the best way for this class, okay? And I hope that just kind of makes it exciting. Some of these things, these topics are kind of dry. I know, it's just like, all right, cool. We're learning how to make a new struct and arranging memory. If you think about it that way, it is kind of boring. But we're solving problems and doing things the fastest way possible. That's pretty cool. All right. So try to think about it that way, and that'll keep you from falling asleep, I think. So yeah, yell at me if you have any questions, but I think that was all that I wanted to say. So we talked about the big three, and then I gave you a little introduction to the data structures that we're going to be studying. And we're going to get real good at implementing them and learning how to analyze them, and I think we'll have some fun. So I think that's where I want to stop for the day. I will see you in the next video.